Hello, my name is Lisa Pivanek, and this is my Physics 2 Lab 3, where we studied the magnetic field of a bar magnet. So, to introduce the experiment, I measured the distance dependence of a magnetic field due to a small bar magnet, and then I also compared my measurements to the distance dependence derived from the equations from the Biot-Savart law, and I made a computational model for the experiment to compare these results. And then the main results that I found from this experiment was that the magnetic dipole moment from my magnet was about 3.22 amperes per meter squared. And then I got an N value of -3 from the Excel data for the distance dependence, meaning the magnetic field depended on 1 over the distance cubed. And then the off-axis field at 45 degrees was experimentally found to be around 1.64 times 10 to the -5th, 1.77 times 10 to the -5th, and 0 Tesla. So some of the main physics concepts that were studied in this lab were magnetic fields and the Biot-Savart law to calculate these magnetic fields. So the magnetic field of a bar magnet looks something like this. It's going out from the north end and it's going into the south end, and it has this circular motion. And then the equations for the magnetic field on axis and perpendicular are given here. And you can see that the on axis magnetic field is twice as large as the perpendicular one. And then you have your magnetic dipole moment, mu, up in the front here. And then the K value is just a constant, it's 1 times 10 to the -7. And then also the concept of superposition, where we can find the net magnetic field from something by the sum of the components. So the actual physical experiment, we were able to ignore the Earth's magnetic field by orienting our phone a certain way in order for the X component to be 0. And then using my phone, I was able to measure the magnetic field from my magnet at various distances from the magnet. And then the equation that was utilized was that our magnetic field is around K, a constant, times R to the nth power. And then by graphing these values and linearizing this equation by taking the natural log of both sides, the N value as well as the magnetic dipole moment could be calculated. And then the equation above is equated to the B equals K2 times the magnetic dipole moment over R cubed. And then additionally, the off-axis magnetic field was measured and compared to the field found in our computational model from GLOSE. So here's some of the data that I found in my physical experiment. We can see that I put my measurement, my magnetometer, a certain distance away from the magnet, and I measured the magnetic field. And then the averages were taken, and the graph was here on the right. And we can see our N value was around -3. And then from this -14, we can calculate the magnetic dipole moment. So here are the main results again. We can also see my off-axis field at 45 degrees is given here. And we can calculate the net field. Here's our X component, and then here's our corrected Y component by subtracting the Y component measured from the Earth. And so our main results overall were this equation right here, which gave us an N of -3, meaning that the magnetic field depended on 1 over R cubed. And then the magnetic dipole moment was once again found to be 3.22 amperes times meters squared. And then the off-axis field again was given here above. This confirmed the Biot-Savart law and the distance dependence of 1 over R cubed. And then the magnetometer, when it was far away, it measured a near 0 magnetic field. And then as it got closer to the magnet, then the measured X component of the magnetic field increased. So then for my glow script code, you can see it here. And this is the equation we utilized for the magnetic field. It's very similar to the Biot-Savart law. It's just we have some R hat and U hat utilized in order for it to work with the glow script model. So we have our physical constant up here. And then the magnetic field B was defined over here with exactly how it's written up on top. And then I also defined the mu that I found in my physical experiment to be 3.22. Here's a continuation. This was just the visualization of the model. You can see all of the arrows. We drew 4 perpendicular and 2 on the axis of the magnet are defined on the right. And then on the left here, we have also the arrow that goes at a 45-degree angle. So here's the final results. We can see that the perpendicular values for our magnetic field are about half the magnitude of the axis ones, and they're in the opposite direction, which makes sense with the Biot-Savart law. And then the 45-degree measurement, we can see that my measurement was given here above, and then the computational model's magnetic field was found here. And these values are pretty similar. They're at least within the same order of magnitude. However, they are off because when I was measuring, there were different magnetic fields where I was measuring, and these likely interfered with my own data. So what if I had oriented my experiment to compensate for magnetic north and had instead laid out my meter stick at some intermediate angle with respect to Earth? magnetic field, how would your results have changed? So essentially, if I did this, then the measured magnetic field would account for both the field from the magnet and the magnetic field from the Earth instead of the values from just the magnetic field of my magnet. And this would have given me entirely different values in the experiment. That would be hard to calculate the true value from just the magnet. And then lastly, if I were to stick two identical magnets together and run the experiment again, how would this change this experiment? And I would say that it would make the magnetic field be larger from the two magnets just from the one magnet. And the directions would all stay the same, as well as the direction of the dipole moment, but the magnitude of the magnetic field would likely approximately double. And then the distances I measured would likely be a lot smaller because that magnetic field is so much stronger. So this was my Physics 2 Lab 3, and thank you.